Check it.
Okay, welcome back. We've been talking about rational functions for the last few sections. A rational anything is a fraction, okay? It's a ratio, a rational function. And the simplest rational function you can have would just be this one right here, y equals 1 over x. So we're going to talk about that, the simplest rational function that we can possibly have. And we're going to graph that. And later on, we're going to get into graphing more complicated rational functions. But this one's going to be our introduction into graphing a rational function. So the thing about a rational function is that it's a fraction. And the thing about a fraction is that you cannot have a 0 in the denominator. So that causes all kinds of weird stuff to happen. Because when you have a denominator, now you have to worry about what's in the denominator and when that denominator is 0. And if the denominator is 0, the function cannot exist there, right? So this creates all kinds of interesting situations. So we're going to talk about the simplest possible rational function once again. And this is called a reciprocal function because it's just simply the reciprocal of x. You take an x, you flip it upside down, it becomes 1 over x. Okay, so let's take a look at this function here and talk about what's going on with it. You have this function y equals 1 over x. And when you're talking about its domain, what is the domain of this function? Well, you look for the red flags. If you remember, the red flags were, can you have a 0 denominator? Can you have a negative inside of a square root? Or can you have a negative or 0 inside of a logarithm? Well, there's no logarithm, there's no square root, so those things we're not worried about. But you can have a 0 denominator if x equals 0. So the domain here, okay, is all real numbers except x equals 0. You can't have x equals 0, right? So what does that mean? Well, your graph is going to exist everywhere, but at x equals 0, there's going to be a vertical asymptote, and we'll get into that in a few minutes. What's the range of this function, by the way? What can the y's do and not do? So let's think about that for a second. This is going to be interesting. What can your y's be? Well, let's put it this way. Your x cannot be 0. Is there any way that y could be 0? Even if x was 0, you'd have 1 over 0, which does not exist. 1 over 0 does not equal 0, so don't even think about that. We already said that x cannot equal 0, right? So it's all real numbers, but x cannot equal 0. So if this is not a 0, this has to be either a positive or negative number, right? Not 0. 1 over any positive number cannot be 0. 1 over any negative number can also not be 0. So there's no way that y could be 0. No possible way. And even if it was 1 over 0, that's still not 0. That's just undefined. So the range would be actually any real number except y equals 0. So y is all real numbers, the range, except y cannot equal 0. So all real numbers except y equals 0, that's the range. So that means there are two things that can't happen. On this function, x can never equal 0 and y can never equal 0. And what that means is that if we had a graph here, your y cannot equal 0, which means you cannot be on the x-axis. That's where y equals 0 right there. So that's going to be a place where you can't touch. And now your x can't equal 0, which means you can't be on the y-axis. You can't be here either. So now you have a situation where you have a function that cannot touch the x-axis and it cannot touch the y-axis. But it will be everywhere else. So where will it be? Well, it can be anywhere in here, or anywhere in here, or anywhere in here, or in here, any one of the 4 quadrants, but it cannot cross those red asymptotes that I just put there. Okay? Now, the x-axis is a horizontal asymptote, and the y-axis is a vertical asymptote. So when your denominator is 0, okay, in this case at x equals 0, you cannot pass through that x value, which means you have a vertical brick wall here. Okay. Now later on we'll learn that you can also have just a little hole in the function, but we're not up to that yet. So anyway, what does this function look like? Well, if you think about it, if you plug in numbers like 1 in for x, make a little table here. 1, 2, 3, 4, 5. Okay. If you plug in a 1 for x, y will be 1 over 1, which is 1. If you plug in a 2 for x, you get 1 over 2, which is 1/2, and then 1/3, and then 1/4, and then 1/5. And what you can see is that as the x gets bigger, the y gets smaller. So that means you're starting at 1, and you're getting really, really, really close. Okay, let me zoom in a little bit on that so you can see that better. And let me try to do that a little better. So at 1, 1, you're here, but then you're going to asymptote you're never actually going to get, because no matter how big this gets, if x is 2 million, 1 over 2 million is still positive. So that's okay. What about if you have x is 1/2? Okay, so I'll have to just make another table here and go the other way. Let's say x is 0.5. Well, 1 divided by 0.5 is actually 2. That means if you're at half, you're actually over here. And what if you're at 0.1? Well, 1 divided by 0.1 is actually 10. That means you're like way up here. And that means what you have is a function that's going to asymptote vertically now. Okay, now that shouldn't be completely vertical looking, but it kind of does. Now, if you have a negative x, if this is negative and this is negative and these are negative, then all the same stuff happens, but it all happens negatively. Meaning all of a sudden all the y's become negative, like that. And what you get is the exact same situation, but you get it down here in the third quadrant. You get the same, okay, the same stuff that's happening up here, you get it over here, and the same stuff that was happening to the right over here is asymptoting to the left over here. And this is y equals 1 over x. So it's got what's called 2 branches actually. And one branch is on this side in the first quadrant, 1 branch is in the third quadrant over here, and you cannot cross x equals 0 or y equals 0. Those are asymptotes, brick walls that you cannot cross. Okay, and when you draw your function, you have to put down your asymptotes as dotted lines, so don't forget that. Okay, so that's the introduction. That's why it behaves the way it does. That's the domain and range. You have a slightly better looking example right here done on Desmos, so you can see how this works. Okay, in this case I made the asymptotes blue. Okay, and here's the actual rendering of the function by Desmos, a better version of it. Okay, you can see it goes through 1, 1 there and 1, 1 there. Okay, that's positive 1, positive 1. This is negative 1, negative 1, but you can see it's doing the exact same thing that I was saying. So now that we have the basics, let's talk about shifting this thing up, down, left, and right. So we've been shifting graphs all year, okay? And there's been kind of a common theme. For instance, if you have y equals x squared, that's your parent function that looks like this, right? How do you move it up and down? Simple. You add a k. Plus 4 will move it up 4, minus 4 will move it down 4, right? So your vertical shift goes on the end like that. However, if you want to move it left and right, the way you did that was, let's start with y equals x squared again. The way you did that was you put parentheses around the x like that, and then you squeezed inside the parentheses a minus h, a negative horizontal shift. So in other words, it becomes x minus h squared like that. If there's a vertical shift, that would be out here plus k. So just to remind you how that worked with parabolas, and it works exactly the same way with all functions. All functions, horizontal shift is next to the x, and the vertical shift is on the end, okay, like this was. So here, we have a reciprocal function. Y equals 1 over x is your parent function, your basic function that I just showed you above. But what's going on if you want to move it up and down? If you want to move it up and down, then add a k vertical shift out here. Okay, that will be your up down. If it's positive, you're going up. If it's negative, you're going down. Now, let's say you want to go left and right. Where would you put that? Well, following the guide that I just laid out for you, you're supposed to put parentheses around the x and then squeeze in a minus h inside the parentheses. Now, since this is the denominator of a fraction, it's already isolated by itself, the parentheses really aren't necessary. So if you take a look over here, this example here, this is your x minus h, and this is your plus k right here. So this is a shift of up 1, and this is a shift of, well, it says minus, but remember, horizontal shifts are always the opposite of what they appear. This is actually a horizontal shift of plus 2, which means to the right 2. And what you can see happening here is we originally had our asymptotes crossing at the center, at the origin, right? We had the horizontal asymptote on the x-axis, we had the vertical asymptote on the y-axis, and they were crossing at the origin. But since we're moving, well, you move your asymptotes first. We did this on previous functions. So we're going to move the asymptotes first and then draw our graph. So in this case, we're going to move our horizontal asymptote up 1 space. So what used to be on the x-axis is now at y equals 1. That's the new asymptote there. And to the right 2, what used to be the y-axis is now moved over to the right 2, and you now have your origin now, your new origin is at 2, 1, which corresponds to this 2 and this 1 here. I know it says negative, but once again, horizontal shifts are the opposite sign. So this is +2, +1. And that's your new origin. And then from there, you draw your asymptotes. And you can draw your, if you're sketching, you can just draw these curves your best, as best you can. Or if you're graphing, then you have to make a table, which we're going to make tables in a few minutes. But for the time being, if we're just doing a quick sketch, draw your asymptotes based on what you see here, and then fill in your curve. So that's what it says over here. If you're sketching, you don't have to worry if there's a number up here. Just treat it all the same, because if that number is a 1 or a 2 or a 3 or a 4, it kind of doesn't matter a whole lot. Matter of fact, I can prove that to you if I just go over to Desmos here. Okay, you can see I have my vertical asymptote there, horizontal asymptote there, and here's my curve, right? And the curve is y = 1/x, which you can see over here. However, if I make this 2/x, let's see if it makes any real difference here. So I'm going to just zoom out a little bit here, and I'm going to make it, instead of 1/x, 2/x, and you can see it doesn't look that much different. It's still the same idea, the same asymptotes. All right, how about if I make it 3/x? Not much different. Still this kind of hyperbolic curve. Okay, the two branches are still one in the third quadrant, one in the second quadrant. So, the number up here, if you're making a sketch, doesn't really matter that much. So if we're sketching, just worry about getting the asymptotes right. Okay. Let's go ahead and do that. Let's make a graph that is, 3 to the right. So that means on the denominator here, I'll put x - 3. And let's make it 2 down, so -2 here. Well, where are the asymptotes now? Well, if the what do you call it? If the horizontal asymptote has moved down 2 spaces, this is going to be y = -2. So that's right there. And if we move over 3 to the right, then this is going to be x = 3. Okay, and hopefully you can see that that's where the asymptotes are. Okay, and changing this number up here from a 4 to a 3 to a 2 to a 1 doesn't make a whole lot of difference in the shape of the graph. I'm changing it here. There's a 5, there's a 6, there's a 7. So for sketching's sake, it doesn't make a whole lot of difference. But if I ask you to graph it, then you need to make a table, and you will use that number. Okay. So it says here sketch. Okay. Since we're sketching, we're not going to worry about drawing the curve perfectly. We just need to get the asymptotes in the right spot. Okay. So where are the asymptotes? Remember, your parent function is y = 1/x. Okay. Y = 1/x. So you say, what did I do to the parent function to get this function right here? Well, obviously I put a -1 here, and that's my k. K is -1. That means down 1. What's my h, my horizontal shift? Well, it's supposed to be x - h. That says +2, so h must be -2, which means to the left 2. So my original asymptotes used to be the x and y axis, but my new asymptotes, they're going to be, well, down 1. The x-axis moves down 1, so it's down here now. And what used to be the y-axis is now to the left 2 spots, so that's over here. Another thing you have to look out for is there a negative right after the equal sign? Because if there's a negative right over here, okay, we've seen this all year long, that means flip the thing upside down. Now, how would you flip this upside down if that were the case? Well, the basic function lives in quadrants 1 and 3. But if you flip it upside down, you would end up in quadrants 2 and 4 instead. Okay. Now there is no flip on this problem, so I'm just going to stick with quadrants 1 and 3 and just do a quick hyperbola here. Okay. Not gonna worry about the top number here at all. Not gonna worry about the exact shape. There you go. That's a sketch. No table required. All right. Let's try the next one here. Next example. This one's got 3 things going on. It's got a vertical shift up 2, right? It's got a horizontal shift. This is going to be h is +1, so to the right 1. But it does this time have the what? The flip. Okay, it's upside down, reflected across the origin. Sorry, across the x-axis. So let's draw our asymptotes first. What used to be the y = 0, the x-axis, is now going to go up 2, and that means our new horizontal asymptote is going to be right here. What used to be our y-axis at x = 0 is now going to be at x = 1. So to the right 1, that's going to be over here. So move your asymptote before you try to draw the graph, whether you're making a table or whether you're just sketching. We are sketching, so we're not going to worry about making a table for this one. And now, once again, if you were sketching, you would just say, all right, well, I got one branch here and one branch here. and I'd be done. But there's a flip. That means these branches are in the wrong quadrant. This one here gets flipped down here like that, so that's gone. And this one down here gets flipped up to here, to this quadrant here, so that's gone. So basically they flip-flop. Instead of quadrants 1 and 3, now they're in quadrants 2 and 4. And that's it. That's how you sketch a reciprocal function. Really, really super easy. And if you're sketching, you don't even worry about what this number is up here because, like I said, it doesn't make that much of a difference when you're sketching. Okay? Now, this next two, we're actually going to graph. We're going to make tables now. We're going to get a little bit more precise. Here it says, notice it says graph. Okay? And I even emphasize it by saying by plotting points, meaning make a table. So this is where we will reach for a calculator. But before we reach for the calculator, let's get our asymptotes in place. So this is a vertical shift of down 4, and this is a horizontal shift of left 2. So draw your asymptotes. Okay, so down 4 means here's the x-axis. We're going to move it down 1, 2, 3, 4, and this is our new x-axis, new horizontal asymptote down here. All right, our vertical asymptote, which used to be the y-axis, is now going to move to the left 2 spaces, so now that's going to go through -2. Instead of being y equals 0, it's x equals -2. And now, is there a flip here? No. So if this were a sketch, which it's not, but if it were a sketch, all you have to do is say, all right, boom and boom, done. That's if it were a sketch, okay? Because you know it's not flipped, you're done. But we're going to actually go ahead and make a real table this time. So let's come over here. Now, what are the x's we cannot use? Okay, what is the domain of this function? Well, the domain is all real numbers except whatever would make the denominator 0. So you cannot have x equals -2. And you can see clearly at x equals -2, there's this big fat red line here, red dotted line, which means we can't be on there anyway. So I'm not going to plug in -2. What I will plug in is something to the right of -2 and some stuff to the left of -2. But I'm not going to plug in -2. So going to the right, let's say, I don't know, the middle of the table here would be -2, like right there. If you're going to the right, then you want to go -1, 0, 1, 2, 3. Okay, that would be going that way, right? If you're going to the left of -2 rather, you'd be -3, -4. So -3, -4. But notice -2, I'm leaving it out because you cannot have that. You can grab a calculator at this point. So this is what our fraction looks like here. 3 divided by, open parentheses, x plus 2. Well, the first x I'm using is -6. So -6 plus 2, close parentheses, and then -4. So we get -4.75. So we can come over here and put in -4.75. Okay, then we can just bring this back and plug in -5 instead. So to spare you from having to watch this entire thing here, I'm going to just fast forward and fill in the table here. Okay, the table's filled in, so let's just plot the points down. -6 kind of -4.75, -1, 2, 3, 4, 5, 6, down 4.75 will be 1, 2, 3, 4.75 would be about there. -5, 5, that would be right about there. -4, 5.5, -4 is right there, 5.5 would be about there. -3, -7, that would be here. And you can kind of see where it is, right? You can see that the graph would be down here like that. And then on the positive side, -1, -1, well, that would be here. 0, -2.5, so 0, -2.5 would be there. 1, -3, that would be right there. 2, -3.25, that'd be right there. And 3, -3.4, like roughly there. You can see that too. That's coming down. It's starting to do the, the asymptoting thing. And on this side, it's going to do the same thing up this way. So once again, you want to put down your asymptotes first, and then after that, you can plug in values for x in your table. Okay. And from there you can get a pretty good idea of what the sketch looks like. Okay, so for these problems they give you the they give you the actual graph, and they ask you to identify the asymptotes, the domain, and the range of the function. So they even give you the equation of the function, so this is pretty easy. Here's your function, f of x equals 2 over x minus 3. Now remember, y equals 1 over x, or f of x equals 1 over x is your parent function. So what's different here? What's different is the -3 on the bottom here. So that means we're moving 3 to the what? 3 to the right. The top number is a 2, but remember I told you that doesn't really matter in terms of shape that much, and we're not really worried about that. So we can ignore the top number here. That just changes the shape ever so slightly, but it's not going to change the asymptotes at all. So we know that we're moving 3 to the right. Is there a vertical shift? And the answer is no, there's no vertical shift. So we're not going up or down. So the horizontal asymptote is still where it is. So let's go ahead and draw that right on top of where it already is. The horizontal asymptote, let's just thicken that marker up a little bit, is still here. That hasn't changed. It's still going to be right there. But the vertical asymptote won't be the y-axis. It's going to be 3 to the right. So 1, 2, 3. This is based on the equation. We can see that. Okay, so just based on this equation, we know where the asymptotes are. So we just identified the two asymptotes. This asymptote is called x equals 3 because it's a vertical line. This is a horizontal line, so it's y equals 0. So that takes care of the asymptotes. What's the domain of this function? Well, you can see this function goes forever and ever and ever in that direction, right? And forever and ever and ever in that direction. The only thing it cannot be, the only x it cannot be is x equals 3. So your domain for this function right here is all real numbers except x equals 3. So domain, all real numbers except x equals 3. What's the range? Well, range means vertically, up and down. This goes down forever, but it never gets past y equals 0 here, right? It never touches that. And on the other side, it goes up forever, but it never, once again, y can never equal 0. So the range is all real numbers except y equals 0. And there you go. That's the asymptotes, domain, and range for that problem there. We'll do one more of these and we'll call it a day. I guess we'll just do 2b here. So if you look at the picture, you can kind of see that there's a separation here, right? You can kind of see that right there. And you can kind of see that there's a vertical asymptote there. But the problem is that the scale makes it hard to tell exactly what those numbers are. But if you look at this, it's very, very clear, okay? You can see from here that this is up 5, so that must be y equals 5. There's your horizontal asymptote. Your vertical asymptote, kind of hard to tell what that is right there, but if you look over here, this is a shift of 1 to the left. So this must be x equals -1. And those are your two asymptotes. Your vertical asymptote is x equals -1. Your horizontal asymptote is y equals 5. What's your domain? All real numbers except, well, you got it right here, x equals -1. And what's your range? All real numbers except this right here, y equals 5. Okay, and that will do it. Have a good one and see you next time.
Check this.